Hello and welcome to this Kangaroo volumetric course. Today we are going to talk about the some volumetric behaviors with Kangaroo. We are going to use Kangaroo 099 and Kangaroo 2. This is the recommendation I wrote also on the announcement for this video course, not because Kangaroo 2 is or Kangaroo 099 are well, one better than the other, but because there are some functionalities that are available in Kangaroo 099 and no longer available in Kangaroo 2, and also because from a learning point of view, Kangaroo 099 allows to better understand some phenomenon happening in Kangaroo. So volumetric behaviors, we are going to explore basically three different aspects. First one is probably the easiest one, even if it is tricky sometimes, it's related with inflatable structures or inflatable bodies. So we're going to work with pressure forces in Kangaroo. The second part will deal with some plane surface or space filling bodies. So we will see how to use Kangaroo to program some growing structure that tends to occupy or fill the area or surface or volume that we make available during the simulation. And the last one will deal with some growth algorithm for mesh. We are going to discuss something quite peculiar actually, so it's going to be a mix between a different mesh representation and some basic scripting to program the so-called differential growth behavior for a mesh. And that would be somehow, well, not difficult, but a little more complex. So today we're going to start with inflatable structures. It's actually they are volumes or bodies that react to some particular forces or goals, in case of Kangaroo 2, which are pressure forces. Now, typically pressure forces are wind and pressure, of course. What we are going to do first is analyze how these pressure forces work in Kangaroo, because normally when you work with Kangaroo, you have forces or goals that act over points or vertices or edges. So typically, for example, anchor points or loads are applied to vertices, while elastic forces are applied to edges. While in case of pressure and wind, they work on the face of the mesh. So in order to better understand this behavior, it's a good thing to go not to Kangaroo 2, where somehow we have a simplified version of these forces. By the way, we can go into Gold's mesh and grab the pressure component and the wind component. These are the standard Kangaroo 2 pressure forces. Of course, there are also other forces, but we are going to consider just these two, and actually we will concentrate mainly on pressure. This is just to understand how things work and what type of behavior they have. And in order to understand this, I'm going to Kangaroo 099 and take the same components, pressure and wind. So you see that there is some difference between these two sets. These are from Kangaroo 2, these are from Kangaroo 099. You see that these look more complex. At least they have much more inputs. And if you take a look at them, you see that both pressure and wind work with 0.1, 0.2, 0.3. And this is because not only pressure forces are applied to a mesh polygon, but also this indicates that this type of forces work on triangular polygons. So 0.1, 0.2, 0.3 are the three vertices, three corners of a triangular face of one mesh. So let's concentrate on pressure. Okay. So if we are working with Kangaroo 2, you see that pressure always asks for a mesh. So this component doesn't need points anymore. It only asks for a mesh and what's the strength you want to use for pressure. Okay, so we will deal with this later because this is what we are going to use. But in order to understand how it works, let's see how pressure is programmed in Kangaroo 099. So let's say we have a basic mesh, which is going to be a mesh plane like this. It asks for point 1, point 2, point 3, how we pass to these values to pressure when we have just one mesh here with 100 faces. Well, we must have access to these faces. Okay, so the first step is deconstructing the mesh. There is another component here, which is mesh explode or something like that. Yes, here it is. And you can directly have access to the faces using this component, each face being a polygon, a mesh, independent mesh. Okay, but in this case, we don't need this actually, because what we need are the 3 points of our mesh. So how do we get to the vertices of each polygon? Once we deconstruct the mesh, we can deconstruct the mesh face. So we take the face and we explode the face. Now, what's the meaning of all this? Why should we explode the face? Because faces is not giving us the polygons, it's giving us the connection scheme of these vertices in order to get to the desired polygon. So for example, if you take the list of vertices that we have here, you see that we have this list with 121 vertices. We have 10 by 10 polygons, so that's 11 by 11 vertices, 121. And faces, the first item of faces is Q0, 1, 12, 11. Okay, so it means that if you want to obtain the first quad, that's the Q stands for quad, you must connect vertex numbers 0, 1, 12, and 11 inside this list. So number 0, 1, 12, and 11. If you connect these 4 points together, then you get the first quad. Now, this is asking for, oh, and by the way, deconstruct face, what it does is take the first point of this connection scheme and send it into corner A. So you will see that here we have 0, 1, 2, 3, 4, 5, 6, 7, etc., etc., which are basically the first values that you see in parentheses here. And then there is corner B, which are the second indices, third indices, and fourth indices of each point you must connect in order to obtain all these quads. So once we have this, remember that we must get to points, not indices. Okay, so we can use this list of indices to obtain all the first vertices of all these faces. So if I use a list item and make a list item of all these vertices using the corner A, these are all the first vertices of each quad face. Corner B, these are the second vertices. Corner C, third vertex. Corner D, fourth vertex. Okay. Now, and in this case, we can eventually create more list items, each one using the corner A, corner B, or corner C of this deconstruct phase. Okay. So in this case, we have first, second, third vertex per face. We also have the corner D, of course, in case of quad panels. Okay. Now we need only 3 points, so this works on triangular faces. So the easiest thing that we can do is use a grasshopper triangulate component that converts each quad, splits each quad into 2 triangles. Now we will see later that this component is not always useful, but in this case, in order to understand how pressure works, we can use it because we are just working with a simple square panel. Okay, so if I take this triangulate and see the mesh, you see that the amount of faces has doubled. It was 100, now it's 200. 2 triangles per quad. Now if I use this, corner D is actually non-existent because we only have 3 vertices, right? So you see that, for example, corner A is 0, 1, 2, 3, 4, 5, corner B 1, 2, 3, 4, 5, corner C is 12, 13, 14, 15, and so on, and D duplicates the result of corner C. So this is totally useless. Okay, we just need the first three values. And so these are the three vertices: first one, second one, and third one. Okay, and once we have access to these three separately, then we can connect them into point 1, point 2, and point 3. And pressure is already set to work in Kangaroo 099 simulation. Okay, so the important consideration is that pressure works on triangular faces. Actually, all the deformations of a quad mesh are considered on the triangular division of quads, as we will see later on during the simulation. And also another thing, pressure level. What's the meaning of pressure level? Pressure level is basically the strength of pressure, but as pressure works at the triangle level or face level, it means that the value that you set here, it will be acting on each one of these polygons. So the actual value of the pressure that you are applying to your body will be multiplied by the number of polygons. Okay, this is something that we will take into account when setting the pressure strength in our Kangaroo 2 simulations. Okay, and the wind works exactly the same. If you want to work with other pressure forces, then the wind is one of them. It is set up exactly like this with three vertices per point. This is in Kangaroo 099. Okay, so let's see how we can work with pressure on a Kangaroo 2 simulation with some let's say considerations about the topology of the mesh. Now, I don't know if you saw the webinar on textile simulation that I published a few, well, actually, I think it was something like 30, 40 days ago, more or less. Anyway, in that webinar, I was considering the structure, the internal structure of a textile body. Now, why it's important now when we are working with pressure? Because the same topological settings of the mesh will affect the deformability and the deformation of the body that we will inflate with pressure. So it's important to understand that we have basically a couple of schemes that are easy to create in Grasshopper, which basically they are all based on quads actually as a starting point. But then if you want to give more continuity, well, if you use just a quad, you will have a deformability that it's oriented like in the horizontal vertical direction. Okay, that's because the edges are usually oriented like this in two different directions. Then there are more complex schemes, like if you want to triangulate your faces, at least you have access to this kind of scheme. Now this scheme is evidently non-symmetrical. Okay, so if you introduce one diagonal, you get this additional deformation direction together with the horizontal and vertical deformation direction, which actually can skew the textile behavior or the body behavior. Okay, and the other scheme is actually taking the quad and creating two diagonals, and this is more symmetrical behavior. This produces a more symmetrical behavior because you are basically determining the deformability or controlling the deformability into the two horizontal vertical direction and also in the two diagonal directions. Okay, so these are the principal schemes. Of course, you can also create more complex schemes, but these are the basics. Okay, so let's see how we can create an inflatable behavior. For now, we are going to use a uniform behavior, okay, and we will discuss this in a while. So I'm going to grab once again the mesh plane, And what I want to do, I want to apply, well, I want to prepare this for inflation behavior. So if I simply, well, actually think about a balloon. Okay, so if you think about a balloon, which is the more common inflatable object that we can imagine, before you inflate the balloon is a soft body, right? So it has no particular shape. Okay, and moreover, it's an elastic body. So if you grab it and you just lift it, it has no particular shape, but it has some consistency. So it can deform, stretch, bend, but it has no particular shape. Um, when you inflate the balloon, what you have when you inflate a balloon, okay, like this one, what you have is the internal pressure of the gas that you are using. It can be air, standard air, or it can be helium. It depends on if you want this balloon to fly away or stay, let's say, floating and falling eventually for the weight of the material. So when you inflate this with gas, what happens is that the internal pressure, if compared to the external pressure, of course, you have that Pi is larger than PE. Okay, so this is what makes the balloon inflate, right? So it means that you have a force acting from the inside of the balloon, okay, like this, for example. And when what happens? That balloon inflates because of its elastic properties. So the balloon material is able to stretch. Normally, it's rubber, right? So it's able to stretch. When the balloon explodes, it means that the elastic resistance of the material has reached its limit. Okay, so there is a internal pressure that is too strong for the elastic resistance, which is basically acting like this to keep the material together. This equilibrium breaks, and then the balloon just rips in some point and explodes. Okay, so you need a balance between elastic force and internal pressure in order for this system to stay, well, to avoid extreme deformation or explosions. Okay, so in order to have this plane converted into an inflatable structure or inflatable body, we need two things basically. First of all, we need elastic force, and secondly, we need pressure. Now, I always recommend all my students that when you work with Kangaroo, unless you are working with rigid bodies where elasticity is not the main feature, if you work with soft bodies, be it whatever, the first thing you might want to program is elasticity. Okay, so let's go into Kangaroo 2. We have a mesh, and we can use in simply the edge length. Now I'm going to give elastic properties to this. And also I want to inflate it, so I take the pressure component. Okay, and that's it. With this, we already have an inflatable body. The problem is that if I just simply connect these things to to a solver, one recommendation when you work with pressure, just always use an initial slider between 0 and 1 and keep it to 0. Okay, you will thank me later. But anyway, if I plug the elastic force to the goal object, you will see that nothing happens because this mesh is actually using a length factor of 1. So all its edges are already in their rest length configuration. So they don't want to neither stretch nor compress. Then comes the pressure. If I plug pressure, nothing happens as well because pressure is set to 0, right? But if I increase this a little, these objects start to fly around. Now, take a look at how this object is behaving. We said it started like floating up, and now it's floating down like this. Okay, it got some deformation because it is an elastic body, and now it keeps on deforming, and it keeps on inflating, right? And it flies away like a feather or something, right? Like a leaf, an elastic leaf. So it's a very nice behavior, but it's not what we want. Now, this is interesting in order to understand how pressure works, because let me grab a toggle in order to stop the simulation and a button so I can reset it and bring this object back to its original position. Okay, so let's go here. Okay, so what's important from a topological point of view is to understand that pressure, remember the example of the balloon, right? So pressure was acting from the inside of the balloon. And if you think about the balloon as a solid normally has, well, topologically speaking, has its positive normal oriented outwards, and negative normal is oriented inward. So positive pressure acts on the inside of the mesh, okay, and not from the outside. So let's consider this mesh plane, right? If I bake this plane and send it to Rhino and turn off the preview of Grasshopper, then we have this object here. If I switch to shaded viewport, you see that I see the white face of this mesh. But if I go downward, you see that it turns orange. This is a visualization adjustment that I do recommend you make. You go into shaded mode, right click on the name of the viewport, and then go into display options, and Rhino settings, Rhino options pops up directly into view display mode shaded, where you can tweak the backface settings parameter, which is in my case a single color for all backfaces, while normally it is used from face settings. So I switch to single color for all backfaces, select a color that you will never use as visualization color, so none of the colors that you would give a standard geometry in Rhino, so you can easily recognize the negative backface of your meshes, of your geometries, right? So each time I see orange, it means I am seeing a backface. And this is valid also for surfaces, not only for meshes, okay? So as you can see, if I, well, consider that our mesh has its normal, positive normal oriented upward, okay? So if I run the simulation, you see that this mesh flies up because pressure is acting on the back face of the mesh, okay? Now, it means also that pressure is not necessarily positive. I can also take pressure and create a slider, symmetrical slider, like between -1. Oh, sorry. I think, yeah, okay. So let's say from, well, 1 is too much in this case, so I'm taking -0.1 to 0.1, okay? So a symmetrical slider, and I initially set it to 0, okay? So if now I release the simulation and eventually start to move this up, you see that this mesh goes up. If I move it down, this mesh goes down. So pressure is not necessarily negative or positive. You can use negative pressure or positive pressure according to the type of behavior you want to obtain. And this basically is, this object is basically receiving a push on the negative faces, in this case positive value, or positive faces, in this case negative values, okay? And it's going to fly around accordingly, okay? You see how you invert the pressure and invert the direction of this behavior, right? So yeah, basically that's all that you need to create inflatable structure. Now in our case, what we want to achieve is an inflatable structure that simply, well, stays in place, doesn't go floating around. So eventually we want to anchor this in a specific position, right? So let's create some anchor points in this case. So we have basically two main possibilities that you can easily program using Kangaroo. If you go into the mesh utility group, you will find two important components, which are mesh corners, and the other one is naked vertices. Okay, so these are very useful for creating anchor point, because mesh corners is actually giving us only the corners of the mesh. Now, corner is a generic word because if you think about, for example, a square, you have 4 corners. But if you think about I don't know, an hexagon, you have 6 corners. And you can in Kangaroo you can use the angle parameter to define what's a corner. So a corner can be any vertex where the concurring edges form a specific angle. Okay, so you can have an hexagon, with six vertices, but no corner because you set the angle in a specific way. Okay, so that's the meaning. But in this case, we only want to eventually anchor this mesh in these four corner points. Okay, the other option is to use the naked vertices. And naked vertices basically extracts all the points or the vertices of the mesh, but into two separate sets: clothed points, naked points. So if you take a look at what are the clothed points, the clothed points are all the points that are not facing the outside. So they are all inner points. That's why they are called clothed. And naked points are these that lie along the edges or along the border of the mesh. So you can eventually anchor this mesh using exactly the naked points. Okay, it depends on what type of behavior you want to achieve. So let's start with one of them. I'm going to get rid of this point container, and I'm going to go into the goals point anchor and use the four corners as anchor point. Now, today I'm going to use a specific method for preparing the simulation. I call it the entwine method, where you see that, for example, another difference between Kangaroo 2 and Kangaroo 099 is that if you grab the solver from Kangaroo Physics, which is the old Kangaroo, force objects must be a list of objects. Okay, while if you go into Kangaroo 2, the solver says you can provide a tree of goal objects. Okay, so let's see what's the advantage of providing a data tree as goal object. Okay, so I'm going to create a data tree using the entwine. And how do I populate the entwine, the data tree branches? Well, normally what I suggest is this: the value or the aspect that you want to concentrate primarily during the simulation, you place it in branch 00. So for example, what do I want to do with this simulation? Well, I want to observe the deformation of the mesh. And in order to do this, I simply need a show component. I send the mesh to the show component, and I want to see the mesh after the simulation. So I bring the mesh into branch 00, and this is the first branch. Okay. And then I do recommend that, well, in Kangaroo there are many goals, right? But you can think about these goals as actions or forces or I don't know, supports or whatever, or boundary conditions, whatever. But in general, there are some goals that have a geometrical preview and some goals that don't have a geometrical preview. So for example, you see that if I plug only the elastic force into the solver is showing us a preview where you see the edges and you see vertices. Now, why you see the edges? Because this edge length is asking for a mesh, okay? But the result are always springs. And how many springs do we have? 220, okay, including the 0. 220. If I take a mesh edge component and I analyze the amount of edges that I have here, I have 40 naked edges, which are the exterior edges, plus 180 interior edges. So total 220. So this component is actually taking all the edges of my mesh and it's converting those edges into springs. Now we will discuss springs also later on between springs in Kangaroo 2 and springs in Kangaroo 099. Actually, we will be working with springs from 099 for particular applications later on. But the important thing is that here we have 220 goals, not just one. Okay, and that's the goal with a geometrical preview, which are these lines. And these vertices here are called the particles or the vertices. And you find them here in the bouncy solver output inside the V output. The particles are basically the points that are considered by Kangaroo as connection point. Okay, we will discuss this later because we have a particular thing to do, and it will be dealing with this thing. So if you create, for example, connection that don't start or end inside one particle, Kangaroo cannot take into account that connection as part of the system. They will be independent connections. So all the connection must converge inside the particles. But anyway, you see that edge length has some geometrical preview. If I grab the anchor point and reset this, you see that there is a geometric preview like vertices. Okay. If I grab a pressure and reset, you see that there is, well, some kind of preview here. But this is interesting. Remember that Kangaroo works, well, pressure tendentially work with the triangular faces. The fact that we miss a vertex here means that we are missing the upper left triangle. Okay, so just keep it in mind. It's just very tricky consideration here. It doesn't affect directly the workflow, but it's important to understand what happens. These vertices here are the vertices, the particle that are generated by applying pressure to the polygons. Okay, and the fact that we miss this, it means that in the end, the very end, this component here always work on triangles. Even if you take a look at this, you have here 100 faces and it says 100 goals. So it looks like it's working on quads, but in the end, the topology is looks like it's always affecting triangles. But anyway, this is something that it's not relevant, not so relevant for us. So what I normally do is, and by the way, even if you have some kind of preview when you connect these things here, well, anchor points don't move during the simulation, so there is no point in visualizing them or taking them into special account. Pressure itself, it's a force, so it's invisible. Okay, particles are here because it's the geometry that has these vertices, is the mesh. So the important mesh, we already have the mesh inside the branch 0, 0. While elastic forces, they have a geometrical preview, right? As you can see, all these lines. And eventually, these are important geometry that we might want to consider after the simulation. So I suggest that you take the elastic forces and bring them inside the tree in a specific branch. Okay, and all the rest, these things, for example, are non-relevant for us. So I take the pressure and the anchor point and send them inside the same branch. Now, it doesn't matter. The fact that we are sending them inside the same branch doesn't affect the simulation, okay, because they are different goals, right? There is a goal pressure and a goal anchor. So Kangaroo can understand what is the anchor point, what is the pressure, even if they come all together, okay? And once we have this entwined, we send it to our bouncy solver. Now, why this method is a good one? Because if you have a simple simulation like this one and you want to concentrate only on the mesh, well, there is no problem. Okay, so you can also use a more simple method to isolate the values after the simulation has ended. The problem with the bouncy solver, or the solver in general, that the output is grouped into one single list. So if you want to access the values, you must exactly know the position of these values. And it depends, for example, on, let's say you want to consider the springs, right? So the amount of springs depend on the initial resolution of this mesh plane. So if you want to extract, for example, the edges from this output, and you see them, they appear as lines, right? So if you want to extract this, you might want to use a list item, for example. So excluding the first item, which is a mesh, you need to extract the following items, which are from item number 1 to how many springs do we have? 220, okay? But if you change the resolution here, then you must change also the list item values, the indices. Well, if you work with the entwine method, you don't have to do this because the elastic or the lines are entering this entwine into a specific branch. So what you can do after preparing this is take a tree statistics component, analyze this tree in order to understand what's the length of each branch. You see, 1, it was the mesh, 220, there was the edges, or the springs, basically, and 104, they are a mix of pressure plus anchor points. Okay, so 100 pressure goals and 4 anchor points. Once you have these values here, then you can take a partition list, take the list of output, and split it using the length of each branch. Remember that in Grasshopper, there is no change in the order of data inside a list or a tree unless you want this to happen. So even if you have a data tree here and a list here, the order of the values inside this list corresponds to the order of the values inside these branches. Okay. So if I use the length of the branches to split the resulting list, I will get a data tree with 1, 220, and 104 like the original one. And then I can explode this, explode tree. And finally, if I turn off everything here, I have access to 0000 is the mesh. 0001 are the lines, which are basically the elastic forces, so the springs. And if you want, but it's not relevant, in 0002, you have the output for pressure and anchor. But remember that pressure and anchor don't have a geometrical preview. Okay, so you see, you get all these null objects. So you might want to simply avoid having this branch visible because it is useless. Okay, so finally, what I want to do, I want to concentrate on the mesh. So I only need branch 0000, but I will take a mesh container, turn off this, and plug the mesh with the mesh, and take a line container and plug the lines to the lines. Okay, so we have lines here and mesh here. I want to concentrate on the mesh, so I turn off the lines and I have only the mesh visible. And now I want to run the simulation. Now I have anchor points here in the four corners, so if I increase the value of the pressure, you see that this thing starts to inflate, but it's anchored to the four corners. Now, one particular consideration here. You might think, okay, so, well, this is actually something that I can also obtain with gravity, right? So, for example, what's the difference if I take, for example, a component like Gauss mesh vertex load, which is very useful if you want to apply gravity to a mesh directly. It works like pressure or like wind as well. It only asks for a mesh and strength. So I want to apply gravity or load to this mesh, vertical load actually. So it is oriented vertically. Okay, apply equal vertical loads to all vertices of a mesh. And strength is set to -0.1. No, I want this strength to be positive in order for this mesh to fall upwards. So I'm going to take a slider between 0 and 1 and plug it here and use it instead of pressure, like this. So if I increase this value here, you see we have more or less the same behavior. More or less, because this is a catenary shape. Okay, while if you work with pressure, you don't have a catenary shape. So now let's take a look, for example, at what happens when you deform this object with these two different things here. So if I, for example, make this object fall a little more, well, I think this is already enough, like this. Okay, so I wait for this to say converge. It should happen anytime soon. Yeah, converge. Take the mesh and bake it in order to have it here in Rhine. Then reset the simulation and substitute the gravity with pressure and run the simulation. So you see that the shape is totally different. Okay, and this is because the pressure and gravity acts in a totally different way. So yeah, you see that these are the two different results that we get from this simulation. Okay, like this. Now, what's the main difference? The main difference is that, once again, vertex loads are applied to vertices, and the direction of a vertical or of a load, any load, but in particular the vertical load, is always vertical. So it doesn't matter how the shape of this mesh is getting deformed, the vertex load is always applied to each vertex and it's pointing perfectly vertically upward. While pressure acts on the polygon, and when the polygon changes its orientation, for example, like this, for example, I have many polygons here. If I have this inclination, pressure is acting on the face in this direction. While vertical load, no matter the deformation, always act like vertically, right? So in this case, pressure will be pushing like this. In this case, pressure will be pushing like this, and so on. So the line of action of pressure changes according to the orientation of the polygon it is applied to. While vertical loads or loads in general, they have a specific and constant application line, right? So they always work in the same direction. So that's why you get this particular behavior here. So that's the main difference between working with pressure and gravity. You get more or less the same behavior because, well, actually it's almost the same, but the final shape is totally different. And another thing is that you can work with positive or negative pressure acting on the negative faces or positive faces, like in this case with negative values for pressure. Okay. Okay, so this is basically already an inflatable structure, but if you want to work with something like this, you might prefer gravity because catenary structures are optimized for resisting to self-weight and gravity, right? And also to eventual loads that you might want to simulate during the Kangaroo simulation. But inflatable structure, this is almost a nonsense because this shape here is not capable of resisting not even its own weight, right? Because this is not a catenary shape. This is not working with compression only, right? So this is not so relevant. Eventually, instead of working with just 4 corner points, let's simulate one of those inflatable structures that are normally used to cover, for example, I don't know, tennis fields or whatever. So in that case, you might want to use naked points as anchor points, right? Like this. So if I do this, you see that the mesh stays anchored along all the boundary of the original mesh. Now in this case, we have some topological problems. I told you that we were going to conduct some topological analysis in case of working with pressure, and this is the moment, right? So if you take a look at these vertices, at the corner vertices, you see that this one is behaving somehow good, right? So you can recognize that there is a diagonal here, which is actually non-visible and non-present in the original mesh. The original mesh only has this quad here, right? But when the mesh deforms, this diagonal edge starts to be visible. This happens each time you have a deformation of a quad. It's very difficult that a quad stays planar, right? So the only way that a quad is planar is that the 4 vertices lie on the same plane. But this is very difficult, and it's very unlikely to happen in a double curvature deformation like this one, okay? So 2 things can happen. If the 4 vertices are not lying on the same plane, considering the diagonal of this mesh, 2 things can happen. So one thing is that, consider the corner quad, right? One thing is that this is the corner, this is an anchor point, and this is an anchor point. So either, and this point here is free to move, right? Because it is not an anchor point, it's an internal, it's a clotted point. So it can move freely according to the resulting forces applied to it, right? But 2 things can happen in this mesh. So either the diagonal division of this quad is like this, or is like this. So if it is like this, then its other endpoint is free to move around, okay? And so this is the case. But if the diagonal has this endpoint and this endpoint, then it is forced to stay on the floor because this is an anchor point and this is an anchor point, right? So it depends on how the polygons or the quads of this mesh are triangulated. And if you take, for example, this vertex here and this vertex here are behaving the same way because the diagonals of this mesh are basically going from the lower bottom corner to the upper corner. And sorry, to the left bottom to the upper right corners, okay? So they are also always going like this. So if you take these other 2 vertices here, you will see that the mesh does this. So the diagonal here goes from this anchor point to this anchor point. So the only thing that this quad can do is basically bend along this diagonal. So one triangle stays on the floor and the other one has this inclination here. And the same thing happens on the other hand. So how do we solve this? And you see that in this case, for example, we must consider, for example, triangular polygons, okay, in order to try and solve this problem. Now, you can use two methods, right? One is a grasshopper native component, which is the triangulate that we already know, okay, like this. But as you can see, the triangulate always gives us the same result. Well, actually, it gives us this result because the mesh is very regular. But later on, we will see that it is not always like this, okay? But in this case, it doesn't solve the problem because we always have the same direction and orientation for our diagonals. So here on the bottom right corner and the upper left corner, we will have the same problem as the previous case, okay? The other thing that we can do is go into the mesh utilities in Kangaroo and take the diagonalized component. So this diagonalized component will generate this kind of mesh based on the diagonals of the original quads. Okay, so it produces a hybrid mesh made up of quads and triangle all around the border. Okay, so you will see here we have, if you take, for example, a deconstruct mesh component, you will see that faces are both Q and T, quads and triangles, okay, and they are mixed together. So if you work with this diagonal mesh, the important thing is that if you consider the corner, as it is based on diagonals, the corner always have the diagonal edge with one endpoint in the corner point, which is an anchor point, and the opposite end is free to move. So if you work with this diagonal mesh here, then you can produce some kind of more regular deformation for your mesh. So for example, if I substitute this diagonal mesh to the actual mesh that I want to deform, and I apply pressure to this diagonal mesh, for example, and I apply gravity to this diagonal mesh here, and I visualize this diagonal mesh as well. The only thing that I cannot do, for example, because it is a problem with this diagonalized component, this diagonalized component alters the topology of the mesh, and it doesn't handle too well the internal or clothed points and naked points. So if I do, for example, this, and I calculate the naked points of my diagonal mesh and take a look at them like this, this is a good result, but it is not always valid. Okay, so it depends on it. This is a buggy component. Okay, so sometimes it doesn't work just properly. So you might want to, for example, increase the resolution of these and eventually try and work with more vertices, and then you see that this is actually emitting points that are not necessarily the naked points. Okay, so naked points are only the point along the edges of the mesh, but when you change this value here, this component just starts to work badly. Okay, as you can see. So in this case, what I am going to do is to use the original mesh to determine the naked points. Why? Because as this diagonalize is based on the original quads and it's only drawing the diagonals, the actual naked points of the diagonalized mesh are coincident with the corner points of the quads, right? So there is no difference between the naked points of the diagonalized mesh and the naked points of this mesh plane. Even if we increase the resolution, if I take this, for example, you will see that no matter what I do here, I have a diagonalized mesh whose naked vertices are coincident with the naked vertices of my mesh plane. Okay, and so if I remove this and go back to the low resolution version, now I have a diagonalized mesh ready to fall upward according to pressure. So if I do this and I take this mesh container in the end, you see that now I get this kind of nice deformation starting from the corner in all the four corners of the mesh. And also we have this kind of perfectly symmetrical behavior because this mesh is totally symmetrical, and it also has symmetrical condition in the corners, so there is no asymmetric, non-symmetrical deformation here. And the thing also that's important to notice is that pressure, as it works perpendicularly to the polygon that we are applying the pressure to, if I, for example, take the pressure and increase it, for example, I increase it to some higher values, it will inflate, 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 and you can see that the final shape is also going outside from the original silhouette that we have from the top viewport. Okay, this is because pressure is actually pushing horizontally, and also in some point it might also start pushing toward the base or the ground floor because of the inclination of these polygons. One recommendation, always try to work with low values for pressure, because pressure can make your simulation explode like this. Okay. Now, remember that we were discussing explosion, and when the simulation explodes, this is some bug you have in Kangaroo. If the simulation explodes and you are in the front viewport, then you can also reset the simulation, but you see that no preview is showing up. But if you go in another viewport, here it is. So this is something that it has to deal with eventually the way that the graphic card is affected by this thing here. But anyway, it's not a big deal. The system is still there, and the preview can be found in another viewport. The next time you open the same definition, it will work properly. So don't work with higher values for pressure. Always start with zero, and then eventually increase it, but very, very gently. Okay. And also, we are considering a strength, an elastic strength of 1, okay? But if we use any value here and multiply this value by the number of polygons of the mesh, it's easy that we overcome the elastic strength, okay? So I do recommend that you always parameterize the elastic strength with something like an 11 slider, which makes the material stiffer and more capable of balancing the pressure, okay? So if I run the simulation again and increase this to 0.2, you see that the deformation is now, well, much more less than before, because this material is more resistant to deformation. Okay, so once you have this, you can also try and increase the values for your pressure force, and you see that as the material is more resistant, then you can produce this kind of deformation with higher values for pressure. But always be gentle when you play with pressure. When you start to see that the system tends to bounce around too much, it means that the system is becoming unstable. So you're reaching the equilibrium between pressure and elastic strength. So the system is about to explode. When you see this, immediately lower the value of pressure. Okay. Now, what we are producing here is a uniform behavior for this inflatable structure. What does it mean? It means that we have the same elastic property for all the extension of the dome or the inflatable body. We have the same pressure applied all over the body. We have eventually a constant vertical load applied to all the vertices of the body. So this is something that produces an extremely uniform behavior for this object. So let's see what happens when we want to produce a non-uniform inflatable structure. Okay. Which is something that it's very common in architectural or engineering studies. Actually, I'm advising several students that they are preparing their thesis on this type of dynamics. Okay, so let's grab something new, like a mesh plane and diagonalize. So let's start from scratch with exactly the same behavior here, and let's, for example, create a non-uniform behavior for this inflatable structure. The easiest way to do this, but we can do two things basically. We can differentiate the pressure. So I want a pressure with a value of X acting on this area, and I want a pressure with a value of Y acting on the other area. But if you want to do this, you need to separate the mesh into two separate sets of polygons, and then you must apply different pressures to the different areas. So you must basically work by separating both the geometric system, like the mesh, and the pressure values. Okay. This is something that is not so common as well, because if you think about an inflatable structure, it's very difficult to differentiate the value of pressure in two different areas of the same body. Okay, so unless you have some isolated chambers here where you can apply two different pressure values, then it's impossible physically, right? So the more common approach to this is basically, instead of affecting pressure, so pressure is going to be one and constant, or well, parametrically variable, but one single value. Okay, you differentiate the properties of the material in order to produce a differentiated behavior. So how can we do this? Well, actually, if you differentiate the material, it means you are acting over the elastic strength. And elastic strength in Kangaroo is represented by two types of goals, mainly, which are the edge length and the length line. Now, edge length is what we've been using so far. So it takes the mesh and assign the same uniform elastic property to all the edges of our mesh. So we cannot work with this, because else we get a uniform behavior, elastic behavior. We must work with this one. And in order to work with this, we need to provide lines. So the edges must be extracted from the mesh and then passed to the length line. How can we do this? Well, it's very simple. We take the mesh edges command. These edges are actually divided into two sets: naked edges, interior edges. Okay. Also, we might want to consider, for example, anchor points and so on, but this is something that we can already do. It's exactly identical to what we did before. But what we need now is basically subdivide this set of edges. I'm going to merge them all together into one line container. Okay, so we have them all here. And what I want to do is differentiate the elastic behavior by using some common attractor structure in Grasshopper. We can work with any type of attractors. We can work with concentrated attractors or diffuse attractor. But in this case, I'm going to start with a simple concentrated attractor, like, for example, an attractor point. And I can take set one point and place this point whatever here. So I have this point, and I want to separate these edges here into two sets according to the distance they have from this point. In order to calculate the distance of each line from this point, we might want to use the curve closest point to project this point onto any of these lines and calculate the distance. But projection in this case has no particular meaning, because if we project this point onto this line, for example, the projection is completely virtual and you only get the end point of this one. So I do prefer create a point on curve per each edge, and so this point is taken as representative of the whole line. Okay, so I have this point cloud here and I have this point, and what I need to do is to calculate the distance between the point cloud and this one. And so I have basically already calculated this the distance between the point, the edges, and the attractor point. Here are the distances. And what comes next is to compare with a smaller than. I'm going to compare these values with a reference value. And this reference value, considering that this mesh measures like 20 by 20, can be easily a slider like 10.00. This is actually outputting a series of true-false values. So I can dispatch my edges, which are the line here. So let me move this a little lower. I can dispatch these edges using this true-false pattern that comes from the smaller than. So as a result, I have line container. Let me turn off everything here but the attractor point. If I consider these are all the edges that lie at a distance that's smaller than 10 millimeters. In this case, we're working with millimeters. So if I decrease this, I can concentrate this set of edges closer to the attractor point. On the other end, I have the edges that are farther from the attractor point, which are these ones here. And now that I have these two separate sets of lines, I can give a particular elastic property to one set and another elastic property to the other set. Okay? Okay, so if I want to give a specific elastic property to the first set, I just use a length line and another length line for the second set. So let's say that, well, the first set is actually the lines that are closer to the attractor point, so it would be this part of the mesh, and I want this part to be more elastic, well, less resistant to deformation. Okay, so I'm going to use for this set of lines a strength of 11, which is what I normally use when I work with pressure by default, and then I tweak this value if needed. And the other set of lines, I want them to be converted into very stiff springs. So I use a 1001 slider, so very high value for the strength of these springs, and it can also be increased if necessary. Okay, so in this case, we can observe that if I take these as elastic property, I will eventually leave this like this and take the pressure, and also take a show component and use this diagonal mesh here for the simulation, so for the show and also for this pressure as well. And for pressure, as I'm going to use an 11 slider and on the other hand a 1001 slider, which is very, very high, I can already set the strength of my pressure to be with something between 0, remember always start with 0 with pressure, and let's say 10. Let's see what happens. Then we need some anchor points. This is the same structures that we saw before. So we can take, for example, the naked vertices of the original mesh, and they are coincident with the naked points of the diagonalized mesh, but this is something that it's problematic when it comes to differentiated clothed points and naked points, as well as interior edges and naked edges. Also in this case, we are working with both naked and interior edges because it is irrelevant for us, but remember that this is also something that can produce some errors during the simulations. So diagonalize is interesting because of the solution that it gives as regard the corners, but it produces some unwanted results or behaviors in the inner part of the mesh. But anyway, here, for example, I have these naked points, and I want to convert the naked points into anchor points. So let's grab the anchor point and plug the naked points, and I have the anchor points already set. So everything is set right now. And I'm going to use the entwine method. So I'm going to send the show into the branch 0, 0, and I'm going to send elastic forces to branch 0, 1. Now I have two separate sets here. So these are the elastic lines, these are the stiff springs. And I want to have them separated after the simulation in order to eventually perform some particular analysis. So I plug them into two separate branches. And then I go and add branches to the entwine, and I send to the last branch all the non-geometrical goals like pressure and anchor points, right? So I can take the solver, I can take a Boolean toggle, I can take a button, and let's say prepare this, and then I can take the three statistics in order to know what's the length of these branches, and finally partition list, and finally explode tree. Okay, so I want to turn off the preview of everything that's here before the simulation. And here you see that I have the preview of my mesh, the elastic edges, which are this set of edges closer to the anchor, to the attractor point, and if you want, we have the stiff springs far from the attractor point. So I take a mesh container for the first output, and I take a line container for this, and another one for this, and I only want to concentrate on the mesh for now. So let's reset the simulation and let's run it. And now if I, for example, give pressure to my system, you see that the first part of the mesh to react is the more elastic part. The rest of the mesh is still elastic, it's very stiff, but it's pulled by the deformation that we get in this more elastic area. Okay. Of course, if I increase the pressure, this thing tends to inflate in the more elastic part. But if you consider it, the stiff part of this object is being pulled like upward. If you want this part to stay more or less flat, you need to increase the stiffness of these springs here. So if I take this and increase it, you see that it tends to pull the body to the ground, okay? Because these lines here are less and less deformable as you increase this element here, this strength here. One thing that you cannot do, for example, right now, is to change the reference number for the smaller than component here. Because if I change this, I create a geometric editing of the system. I change the amount of elastic lines from stiff lines. Okay, and this is something that Kangaroo doesn't like. So if you want to do this geometric change on your system, you must stop the simulation and do whatever you want. So I will decrease the reference value for the distance and reset and run the simulation again. So I have a more concentrated deformation here. Okay, and this is just one possibility that we have. What happens, for example, if we want to work with multiple attractor points? Okay, so for example, what happens if I want this mesh to deform only with correspondence to the 4 corners? Okay, we have the original mesh plane here. We can grab the mesh corner component, have access to these 4 corners here, and I want to use them as attractor points, so I can plug them here, right, directly. The problem is that if I do this, this distance is actually working not properly. Okay, so distance is basically the evaluation of the distance between this set of points and this set of point B, right? So if I grab a line start point to end point and replicate this situation, you can easily see that the way that these distances are being calculated is not the proper way, because all these points are related to this vertex here. So what happens here is that we are comparing a list of 440 values with a list of 4 values. And so due to the longest list method in Grasshopper, the first element interacts with the first element, second with second, third with third, fourth with fourth, and all the remaining elements here will interact with the 4th element. So we don't want this. We want to calculate the distance of all these points here and each of these attractor points. So we must graft this. And if we graft this, now we have 440 distances per each attractor point. Now, what I want to do here is not to consider the distances grouped by attractor point, because if we do this, we will have, for example, if we consider any of these midpoint for the edges, to each of these midpoints, we will have 4 distances associated to it. Okay. But what I want to understand, if this point is close enough or too far from any of these 4 points. So I don't need to have the distances grouped by attractor point. I have to have the distances grouped by edge. So this can be done, for example, by flipping the matrix. Now I can flip the matrix here, or you see that we have 440 into elements into one branch, and here we have 440 elements into one branch as well. This is actually telling us that you see that in our set of points or edges, you have some trues and some false. The true corresponds to the edge that is close to the attractor that we are considering, which is the first corner of the mesh. Okay, and then we go and have the second set of point. It starts from here. We have another series of false, which are the same edges but related to another attractor point, so another corner. So the distribution of true false changes, right? So if we want to group the true false values by edge, then in this case you must flip this matrix. And now we have the same amount of values, 1760, 1760, but they are grouped 4 per each branch. So each branch contains the true falses related to the relationship between one edge and the four attractor point. So if I have this and I want to understand if one specific edge is close to at least one attractor point, then I must do something with these values here. So this is actually a set of true false. Okay, so if I find what can happen inside this list here is that either we have four falses, it means that the edge is far from any or from each of the attractor point, or some true will start to appear. Now, if we have a true appearing, it means that this edge, the correspondent edge, is close to at least one of the attractor points, and I want to maintain it. So we must basically convert this into a true, okay? So the dispatch will send that edge into the list A. While if we have four falses, then the dispatch must send it to list B, so it must receive a false. Okay. Now this is pretty easy because these are true false values. True false, on off 1 0 are all well, basically different presentations of one single concept, okay, which is logic. So if I take an integer container and plug this here, you see that now if I take a look at what happens, even if it is not receiving integer value, it converts false into 0 and true into 1. So now it's easy. If I have, for example, if I perform a mass addition of these numbers here, two things can happen. Either I get 1 or I get 0. If I get 1, it's because this edge is closer to at least one of the attractor points. If I get 0, it means that the edge is far from each of the attractor points. And so if I flatten this result, I will have a list of 1 0, 4 4 0 values. I have 4 4 0 lines, and so I use this 1 0 as dispatch pattern. Remember that as we can convert true false into 1 0, we can use 1 0 as dispatch pattern. Okay, and so in this case we will have the set of lines that are closer to our corner points and the set of lines that are far from the attractor points. Okay, so everything goes back to normal, and I can basically deform this like mainly in the four corners. Okay, and I can also increase pressure if I want, or make this pressure negative. I can do whatever we already know. Okay, and if I decrease the elastic resistance of the deformable edges, then I can easily deform this more and more. And of course, if I also increase the initial mesh resolution, like for example placing here an 1111, set this to 20, which means a mesh with 400 polygons, and then I reset the simulation. Always reset the simulation, is good to do this. So we start to have a more high resolution behavior for our mesh. Okay. Now remember that we are considering a reference distance that starts from the point and basically creates some kind of circle around. So if we want to reach the inner part, we must consider the diagonal, half the diagonal of the square, as the reference distance. Okay, so basically it is something like 10. Now this is another parameter that I cannot edit on the fly, because this parameter here would affect the amount of elastic edges and the amount of rigid edges. So this is a change in the geometric system for Kangaroo. And you cannot do this on the fly, because if you do this, Kangaroo is no longer able to sort the elements properly. So in this case, each time you must perform some kind of a geometric edit to the system, you must stop the simulation and then change the values that you want to change, like in this case, the reference distance, reset the simulation again, and run it. Okay, and so we have this kind of program deformation for our system based on pressure. and there is a less elastic part in the inner part that in this case it's subject to some important tension because there are four parts that are being inflated and they are pulling the inner part quite much. Even if this is not elastic, it's going to maintain its rigidity but bring this to a higher level. Okay, and so you can program the deformation occurring on this body via the pressure parameter, the pressure goal. Okay, and of course we can also decrease the amount of pressure and see how this affects this body. Now this change here doesn't affect the geometry. It only says that when the pressure acts, it acts with a different intensity. Also, once you have the separation between elastic line and rigid lines, in that case, basically you simply can edit the intensity, the strength of these forces. This is not affecting the geometric aspect of the system. Okay, so if I do this, I am only saying that my elastic edges are more elastic. You see that the rigid part stays more or less undeformed. Okay, it's just being pulled higher. And then you can program this kind of nice behavior for your meshes. And one last consideration is that this type of object, this type of shape is very nice, and it's very difficult to obtain it with a direct modeling. So even you can also use this method here, like inflatable structure, to create some nice geometry. But in that case, you must pay attention to few details. For example, even if you work with a high resolution mesh, like I'm doing right now, this has become a mesh with 1000 faces. So it's quite high resolution for a square panel. You always get this faceted aspect, okay, because you're working with a mesh. If you want to get rid of this, the only way that you can get rid of this is by applying some smoothing algorithm, okay? And so once you have the mesh, you can use like, I don't know, like some Catmull-Clark or loop subdivision, because we said that it not only increase the amount of faces, but also smoothen the final result. So if I do this, I'm increasing the amount of polygons, but I'm also smoothing the orientation. So this is way smoother than the previous result. And the nice thing is that because we are working with elastic bodies, you have this kind of wrinkles happening over the bodies themselves. You always must pay attention to what happens to the vertices, because you see that this is a smoothing algorithm. And so you see that it is taking the final mesh away from the anchor point. If you don't want this to happen, you must specify that the smooth naked edges is corner fixed. So corner fixed, oh, sorry, it's not working this time because you have to decide fixed. This is some kind of tricky aspect because it depends on the topology of the mesh that you are using. And this is a diagonalized mesh. So corners have become different than the original corners of the original mesh. So just switch between the corner fixed, and you will find the proper solution. And the other thing is you must avoid self-intersections. So when you work with pressure, it's very common to obtain self-intersections because, well, Kangaroo doesn't care about self-intersection at all, unless you specify that you don't want self-intersection. So what can happen here, for example, when you have this separated part inflating independently from the other, one part can expand and the other part can expand, and they start to overlap in the in-between, okay? So if you want to avoid this, I suggest that you consider using some kind of collision control. The simplest one is using spherical light. So you can take this spherical light here and take all the vertices of your mesh and specify a collision radius. So for example, if we take, well, in this case, let me double check because let me reset this and let me double check that these vertices also belong to these diagonalized. Oh yeah, actually what we are seeing is the smoothened mesh, but this is the original mesh. So vertices corresponds to the actual faces. What I want to double check is that if we take the naked the vertices from the original mesh Well, actually, they correspond to the actual vertices of our diagonalized mesh. Okay, so we can also take these vertices here, with this mesh here, and take the famous naked vertices, because we have access to the clothed points. Now, I'm also going to explain why am I doing this. Okay, so we have the clothed points, which are only the inner points for inner vertices for our mesh, and I want to apply some collision only to these points. Now, I'm doing this because the spherical light doesn't like working with anchor points. So spherical light is a force that keeps points separated using a radius. Okay, so imagine that there is a point here and a point here, and basically you are considering a radius that avoids this point to be coincident with the other one. So it converts each point into a sphere with a given radius, and this radius must be equal for all the points. So there is no possibility to work with different radiuses. Okay, we will discuss this later in a different scenario, different type of scripting or behavior that we want to program. So in this case, imagine that each point becomes a sphere with this radius. And so you have this kind of physical separation between the points. And if you do this, you cannot do this with anchor points, because sometimes the spherical light tends to separate the points from each other. But if they are anchor points, this is impossible. And this is something that Kangaroo doesn't accept. So basically what I'm going to do, I'm applying this spherical light only to clothed points, because my mesh is being anchored only on the edges. So I'm not working with the naked points, I'm just working with the inner vertices. And when we run the simulation, another important thing is that when we run the simulation, we see that the problem, the overlapping phases, are more likely to happen in these areas, okay? So we must also take into account what's the actual separation between these vertices, okay? And if we go into the top viewport, you see that if compared to one square of our grid, we are considering something like decimals values, okay? So the radius for my spherical light must be something very, very small. So I will take 1.000 as the radius, which I know is going to be too much, because one of radius means like this distance between the vertices. So this is going to also expand the mesh too much. Remember that when you work with the pressure, things are more delicate than the usual. So I'm going to decrease this initially to 0, and stop the simulation, reset the simulation, and apply this to the non-geometrical goals. Okay, so what happens now that we are working with pressure? Pressure tends to expand the mesh, and it's only balanced actually by the elastic properties. Okay, when I add a spherical light, the spherical light tends to separate the vertices as well as the pressure. So this force here, this goal, acts like to reinforce the pressure. And if the combined action of these two is not balanced by the elastic resistance, then the mesh can explode. Okay? So when you work with the spherical light, also like with pressure, try to be gentle when creating this kind of changes, because when these start to work, you will see it immediately to 0.2, 0.3. Now the mesh is starting to react. I already see it because the mesh keeps on moving, even if it already reached an equilibrium between pressure and elastic force. So this is more or less the limit, okay? So 0.5, okay? If I tend to increase this, you see that the mesh starts to inflate more. Actually, it is not inflating more. The vertices are separating from each other. Now, this is good for this particular portion of my mesh. You see that this is stretching and smoothing, okay, like the aspect of the mesh. If I decrease this, I am back to the original situation where my vertices in this area can tend to overlap more, okay? So this is a control that allows the mesh to, let's say, is kept separated, okay? So this tends to avoid self-intersections, okay? But also you see that in these parts, this is acting like it's counterproductive because this is creating this kind of, the mesh here, if you want to see it like in detail, is falling down and then it's going up. So it falls down and then goes up. And in this case, for example, it's impossible to avoid self-intersections, as you can see, okay? And in order to avoid this, the self-collision must be taken into account at the very beginning of the simulation, okay? So if I run this, you see that in this case, this phenomenon is no longer happening, okay? But this also affects the final result. Because in this case, for example, as this collision is happening from the very beginning, the mesh is not capable of rising up in the inner part because the collision is keeping it low in these areas, okay? Of course, the system is adapting, you see, as long as it says running, this thing is deforming, okay? So eventually, it might succeed into going up here, and this going up means that it's going to pull also these valleys here, okay? So I don't know exactly what configuration will be the final one, but you see that we get this kind of nice behavior. And this behavior is like basically having, let's go over here, like these edges here are the rigid part. So it's like applying some taping or some kind of differentiated material in the inner part of this inflatable object that keeps it under control and lets it deform this way, okay? So inflatable structures are not only like uniform material subject to uniform goals or uniform forces. The interesting part is when you start to differentiate the properties of the material or the pressure itself, okay? So this is one approach. We are differentiating this behavior by applying different elastic properties to different parts of the material. And of course, now we are working with points, attractor points, but we can also work with, I don't know, NURBS curve. So if I say I want a NURBS curve, parametric NURBS curve, like set multiple points, and I want to apply a differentiated pressure along this line here, like a S along the body of my mesh. And then I need the distance once again, okay? So I need to change approach here. If I want to work with attractor points, distance is good enough. But if I want to work with a curve or with curves, actually, I can no longer work with distance because we have, once again, we use the point on curve to calculate the distance between the attractor point and the edges. Here we have another time we have a point cloud and another curve. So I'm going to use a curve closest point in order to project all the point cloud onto this attractor. And this gives us the distance. So if you want to work with an attractor curve, you must switch from distance to curve closest point. And in this case, the distance come up from this value here. I just plug it like here to this comparison, and we are already set because we are getting this 5,400, 5,400. Problem is that, let me double check. Okay, we are getting this. Oh, well, actually, this has become useless because we're only working with one attractor. But nevertheless, we want this to be valid in general. So what this is saying is that all of my edges are closer than this distance. And this is something that it's perfectly understandable because once that I'm using this curve here, there is no edge inside this mesh that is farther than 10. So if you imagine this line here and you create an offset, for example, of this line using 10 as a distance, you already reach this part here. And if you go the other side, then you will reach the other side. So there is no edge which is farther than 10. But if I start to decrease this value, like 5 more or less, you will see that here we have these far edges. Okay, so in this case, what I'm going to do, as this attractor is occupying most of the extension of my mesh, I'm going to reduce the distance like to 2. Okay, so we have rigidity programmed with corresponds to all this set of edges, and elastic part is going to be this one. Okay, and this is going to be a little more interesting because the deformation is going to happen along a path, and this is going to be driven by pressure, also with some self-collision. Okay, now this self-collision is exaggerated, like 1 is way too much, but you can see how the pressure in this case is producing some kind of totally controlled behavior along this attractor. Of course, we can also decrease, once we have programmed the presence of the self-collision, we can also decrease the value in order to leave the deformation free of occurring in areas where there is no need for self-collision control. While in this area, this value is already enough. Okay, so the reason for this spherical light is to avoid self-intersection, remember. Okay, so we are producing this kind of, I don't know, cake, who knows. Okay, and you can also work with more than one curve attractor. Okay, but this is just adjusting the this part here, which, by the way, should already be working fine if you consider more than one curve. The only thing is that if you consider more than one attractor curve, you must graft the curve closest point. Okay, so let's graft this. And now you can consider more than one attractor curve, because here you would have comparison, flip matrix, integer, and mass addition with flatten. So everything is back to normal with the same amount of values here at the end. Okay, so this is a general definition that can work with more attractor points or more attractor curves. You can also switch to, in order to program a differentiated elastic behavior, or inflatable behavior, you can also program this with diffused attractor. Now, points and curves are concentrated attractor because they're physically present in one specific position. Okay. But you can also work with a diffuse attractor, which is basically working with some image sampler. So you can paint an image in order to differentiate the elastic property or elastic resistance of your material. And in that case, pressure will work differently according to the different elastic behavior, which can be way more complex than working with the concentrated attractors. So I leave it like a new development that you can easily do by yourself. Is just painting an image in grayscale and associating white to, I don't know, more elastic edges and black to less elastic edges. So in that case, you can simply use any editing photo editing program to create the correspondent distribution of elasticity or rigidity along your mesh. Okay, so this is something that I would say is an indirect approach to differentiated behavior for inflatable structure. Now let's go and analyze a direct approach, okay, which is...
Giancarlo?
Yeah.
Excuse me. It's me, Ariel.
Yeah, Ariel.
I have a doubt in the beginning of the definition in this case. I tried to recreate it.
Yeah.
But my mesh exploded immediately. I don't know what kind of elastic property you're using for this, because
yeah,
I feel like
if it explodes immediately, what I would suggest is that you increase the strength for the elastic properties. So you see you see that rigidity means very high values.
Okay.
But also elastic property for the elastic part must be high enough to contrast the amount of pressure that we are giving. Remember that even if you see that here, the elastic strength is 8.4, while pressure is 2.5, right? So this is way below than this value. But remember that this is going to multiply by the amount of polygons that you have in your mesh. So
Okay.
this is already a very high value for pressure. Okay. Now, when it comes to well, let's discuss this with the following example. Okay. When it comes to direct control, so what I'm going to do right now, actually, I'm going to switch to a more complex mesh. Okay, so I want to work with a more complex mesh, and in order to do this, we can do several things actually. But working with Rhino is it's not a good thing in order to create an initial mesh configuration. In my case, what I would do in this case would be to switch to Blender, create the mesh that I want with a precise topological control, and then import this mesh into Rhino. But I need to spend a little time here to create the proper mesh. So I'm going to use the 3D face method that we already saw. Just consider that you always need quad faces, and all well, actually, it doesn't matter exactly the orientation, because once we join them all together into one single solid, all the orientation would be flipped with positive normal pointing outward. Okay, so in this case, you can also avoid considering the orientation of your initial polygons, but I do recommend that you always take into account the orientation. Okay, so what I'm going to do, I'm going to create some kind of let's say X structure, like this, and I'm also going to array power this, like with I don't know, 3 branches, yeah, like this. Well, no, 4 branches, in order to have a more regular topology, like 4, like this. And what I'm going to do, I'm going to move them so that they have a more regular distribution. Let's say like here, and this is going to be like here, and this is going to be like here. And then I'm going to create another 3D face in the center. And then I'm going to join these all together with the missing polygon, always counterclockwise, as you can see. Okay, this is just the first step. Now what I need to do is to create this well, actually, eventually we can also work with a more simple scenario. Yeah, let's try to do this with a more direct approach, like creating a mesh plane with, well, 10 by 10, no, I would say rather not even number of polygons, but odd number of polygons. And eventually less polygons, because you can increase the amount of polygons inside Grasshopper. So 5 by 5. Yeah, let's create a more regular thing here. Okay, so what I want 2 center stripes, 2 middle stripes of polygons in the center of my mesh. Okay, well, actually, now that well, if I take this approach, why not create exactly one mesh box? So I want 5 in X, 5 in Y, and as regards Z, I only need 1 polygon. Yeah, so let's create this like this, and this is going to be the initial width by depth, and this is going to be the thickness, something like this. Okay, now in this case, for example, it's impossible to obtain as this is a solid shape. Normally, every program tends to orient all the polygons or the faces with the positive normal pointing outward. Okay, so you see that there is no orange face in this case. So this is my original mesh. I'm going to take this mesh and import it into Grasshopper. And as this is a quad mesh, I can also go back into Kangaroo 099 and take the quad divide and do something like this. I want a higher resolution, okay? But for now, I'm going to stick to the original topology. So what I want to differentiate the behavior for this mesh, but I want to do this exactly in a controlled way. So first of all, let's reduce the thickness of this thing. So I want it to be flat-ish somehow, like this. And as I didn't internalize the data, now you see that this is the actual mesh that I have inside Grasshopper. So what we can do with this is eventually differentiate its elastic properties in order to program the behavior of pressure. So for example, let's say that we want the central stripe of this mesh to be more stiff than the corners. And this in real life corresponds to apply some taping along the center lines of this object, okay? So what I'm going to do, I'm going to simulate that the center part is this is a uniform material, so there is no initial difference in the behavior of this material, but I'm going to simulate the presence of some rigid material applied onto this surface, like taping, okay? So this is used to control or to program the deformability of the material when you apply pressure. So what happens, how can I manage this, this thing? Well, always working with a tractor, this is the easiest way. Unless you want to create a non-parametric workflow, and in that case, you can simply decide by hand where you want this particular deformability to happen, okay? But I tend to keep things parametric at the beginning, and in any moment you can switch to a non-parametric workflow if you need it. So what I'm going to do, I will consider the high resolution version for the simulation, but not for the programming of the attractor, okay? So for example, if I need to define some attractor rules, in this case, I would say, well, let's take some lines. I would say set multiple lines, for example, and we can work in different ways. We can, for example, take one line more or less here at the center, like one here and one here. Or we can work with lines that lie, with correspondence to the lines of edges that we want to differentiate, like this and this. Now, what's the best approach? I think that as we are going to work with a higher resolution version, which doesn't correspond to this set of edges, I would suggest that we create multiple lines, but like axis of our mesh, like this. Because in this case, we can work considering a distance from the attractors, okay? And it doesn't matter how high is the resolution, because we can always, working with the distance, we can also always involve more edges or more set of edges expanding from these two initial lines. Now, if we want to be more precise, in order to avoid this imprecision when you draw these lines in Rhino, you can start from the very volume of your mesh. Now we are working with a box, so it's very simple to extract some center lines, okay? We can start, for example, from the mesh volume and find our mesh centroid, which is this one, and from here we can draw lines, okay? So if you want to be more precise, you can use some parametric method here in order to create these lines. So starting from here, we can create, I don't know, some SDL line, starting from this centroid along the X direction, using a whatever length that we might want to use. For example, I don't know, in this case, I would say an 11 slider is enough to create enough extension. And what I want is also to use a negative for this in order to go the other side, okay? And so if I plug both of these, I'm getting to these two lines that I can join together with a join curve. So I got this. And we can also try to do this with the Y direction. So we can also include a Y direction like here. But if you do this, you see that here there is a data interaction that it's basically splitting the problem into two different directions. If you want this to happen in both directions, you eventually must graft these vectors here. So everything is happening in both directions. And if everything works just fine, we should have, well, actually, we are getting two different lines. And I think this is joining like in corners. Okay, so if this happens, you flatten this, and now we have two curves, two linear curves. This is one, and this is the other. Okay, so now everything is working properly. We have the two center lines that we needed, and we have the box mesh, like the original mesh. And so once we have this, we can start working with the high resolution version. So I'm going to hide this. Okay, I'm going to turn off the preview of the edges, Control M, so I can see clearly what's happening. Because I'm going to calculate the mesh edges. One consideration, as we are working with a quad divide, there is one problem, just one problem with this mesh. The quad divide is also splitting the height. We had just one quad, okay? But now this one quad is being splitted into 5 by 5 polygons. And so we have very small edges vertically along the side of this mesh. This can be a problem because when we program elastic properties for these edges here, either they tend to expand. So if they expand, this part here is going to expand more vertically, okay? But anyway, we will take into account this problem later on, and eventually adjust the mesh that we created in Rhino, not in Grasshopper. So we have these edges here, and the process is absolutely the same. Point on curve for our, well, actually, we don't have any naked edges here because this is a solid mesh. So all the edges are interior edges. And so once we have the point cloud, we can finally understand what are the closest edges to our center lines, because I want to give a specific property to those edges. So I curve closest point, this point cloud, onto my curves. Remember that you must graph these curves else you get this kind of weird interaction. So now we have all the vertices projected onto each of the two center lines, and we have two sets of distances. So we want to compare this with a smaller than, like with a 10 slider. And what we want is to get rid, by calling pattern, get rid of the corresponding edges, interior edges, according to this smaller than. Now, if we do this, you see that everything well, seems to work perfectly fine. I would suggest that you, let's say, work safely by, let's say, adjusting this call pattern, because remember that you are using 3,500 lines with two sets of 3,500 values. Okay, so this is not good, because either you see that, like from a visual point of view, everything seems to work fine, but the risk is that here in this area, you have double the amount of edges that you need, because these edges are close to this line and this line. So they appear twice in the result of this call pattern, okay? So I would recommend that you avoid this phenomenon here by considering just one set of two falses here. So it's like we did before, flip matrix, group the true false by edge and not by attractor, okay? And then once you have this thing here, you mass addition, which is the quickest way of doing this, and you will get a set of zeros and one. You can flatten this, and you can use this as call pattern, okay? So here we have 792, okay, values. While if I don't do this, if I use exactly the smaller than pattern, in total, we have 840. So we have duplicated edges. And this is the worst thing that you can do, because if you have duplicated edges, you will have 2 times elastic properties, 2 times any property, any goal that you apply with Kangaroo applied onto this mesh. Okay, so just use this method here in order to get rid of duplicated objects. Yeah, so that's it. We have our meshes divided. Well, actually, instead of using a call, I would use a dispatch. So to have both sets of edges. So let me double check with a line container. These are the far edges. Perfect. And that's it, because from now on we can work with what we already know. Okay, so we can decide, for example, the tipping that we are applying, if it involves only the central edges, like for example like this, while all the rest of the edges, which are these, which are left free from the attractor, they can work like with the pressure that we want to apply. So for example, let's say that I want to apply some taping only in the center lines, okay? And I leave all the rest free, like this. So in this case, what I want to do, the center lines are these lines here, or these lines here, okay? So this is where the taping is taking place. So I want these lines to be stiff. So I take in Kangaroo 2, I'm taking the length line container, and I give this line A very stiff behavior, like with a 1001 slider. So they want to have this rest length, which is the original length, and they want to maintain their length with this strength. So they are very strong. And then I take another length line for the line B, and take a strength of, which can be quite small. With 11 slider is more than enough. Remember, don't use small values when you work with pressure for the elastic properties, okay? Because if you increase the value of pressure, it's very easy that the elastic property just is not enough to contrast this the amount of pressure, okay? Then we go into Gold's mesh and take the pressure. There is no need to use edge length, because we already defined the elastic property by working with each edge. So our initial mesh is this one. I'm going to plug it into the pressure. Remember that now we are working with quite a high resolution version, so it's 750 faces. So the value that you set here is going to multiply by that value. So remember to use very small values initially, and eventually you can increase this the range of this slider at more than one later on. Okay. Now what I want to do, well, actually, if I simply run the simulation right now, so if I take my solver with a toggle, with a reset button, and I repeat the entwine method, it's the more efficient way, remember? So I only miss a show because I want to see the behavior of my initial mesh, range 0, 0. And then eventually I want to see the rigid edges, well, elastic edges and rigid edges. And then I will apply a non-geometrical goal to 0, 3, like pressure, okay? Then everything is sent to the solver, and then I tree statistics in order to obtain the length of each branch. And then I partition list and explode tree. So this is something that, but there are actually some plugins. I don't know what was the name of that plugin that allows to store some group of components. So each time you need that group of components, you can simply click on that plugin. It had some kind of the icon was something like a bin, like this, like a repository of definition or small scripts. And then you have access to whole set of or group of components. I would create a group of components with this, and it's cross definitions, so you can use it in each definition that you are creating at any time. You store this group, this block here inside that plugin, and then you have it available inside each new script that you create. So it's very, very useful, but I don't remember the name. But anyway, you see that now we have the mesh and the rigid, the elastic edges here, and these are the rigid edges. Somebody knows it? Let me see. Cluster? No, no. Cluster is a way in Grasshopper to group component inside one single block, one single node, uh, but it always works inside your script. So if I create a cluster with this inside this definition, this cluster will not be available in a new script. While this plugin that I'm saying is basically a Grasshopper component where you store a group of components and you have it available inside each script that you create. Okay, but anyway, eventually I will look for it and publish this in the description of this video on YouTube. So it will be available later on. Yeah, so I want to concentrate for now only on the mesh. Okay, so here it is. And let's recover the edges visibility. Remember that we have these edges here, okay? And these edges are far from the attractor. So they are kept elastic. So they can expand, okay? So if I run the simulation, now nothing happens because I have 0 for the pressure, okay? But if I increase the value of pressure, this thing starts to deform. It's like a pillow somehow. You see that it's deforming, but mostly outside from the presence of the tape. The tape is keeping this thing more stiff along these edges here. Okay, so we get this kind of nice deformation. But this deformation is occurring in a very free way because there is no, basically no anchor for this. So we are only getting a pillow. Okay, which is nice. I mean, you can use Kangaroo to model this kind of complex objects. I find it very useful, for example, for those of you who also are into visualization. One of the most difficult things to model in 3D are textiles and inflatables, like blankets or towels or cushions or pillows or whatever. You know. So in this case, you can use Kangaroo for this kind of particular applications. But anyway, this is the type of deformation that we get because of the taping that we applied to this object. But as there is no anchor, this object is free of moving around in space and inflating however it wants, okay? What happens if I start to provide some anchors to this object, okay? So what happens if I go back to this configuration and eventually start to anchor or place some anchor points? So, for example, I kept the original object in Rhino because I wanted to manually position this anchor point. I don't want to waste time with too many constructions here in Grasshopper to isolate the desired geometry that I want to use. So I'm just using the vertex snap here to place my points, set multiple points, and I'm going to use this vertex here, this vertex, and this one. And I want to use them as anchor points. Okay, so I'm going to hide this mesh again, and I'm going to anchor my mesh using just these 4 points here. Non-geometrical preview, so it can go together with pressure. I don't care about it. And run this simulation again by increasing the value of pressure. Now I have 4 anchor points, so those points cannot move. So this object is forced to stay horizontal, okay? It can still expand vertically, okay, freely. So this is not enough in this case. See how the elastic resistance, in case I eliminate the pressure, keeps these springs here from deforming back, you see? So this is not going back to flat because, let's take a look. This deformation here, this bending of the 4 sides, allow these edges to maintain the original length, but maintain also these arc-like shapes, like here and also at the bottom of the structure. Okay, so this is never going back to its original configuration, and it has this kind of a particular shape. But anyway, I'm going to reset this, and what I'm going to do, I'm going to add some floor. Okay, so this object will be only capable of expanding upward. We can do this like using the standard floor component from Kangaroo. But in my case, for example, this object lies at a height of 3 point something. Okay, so if I place a floor, automatically the floor will be placed at the XY orientation of the original world coordinate system. So this object would be able to expand a little down and then, let's say, encounter the floor. But I want this floor to be at this height. So I'm going to take a different goal, which is a what can we use? Let me see. No, maybe a solid point collide. Yeah, maybe a solid point collide, or we can also use a solid plane collide, which is when eventually, let's say, well, no, because we are not working with rigid objects. We should define this box as a rigid body, but we don't want, because we want some pressure working on it. So see, this the workflow that you decide also determines some limitations in the components that you can use. So yeah, I'm forced to use the solid point collide, and therefore I must take all the vertices of my mesh and make them collide with another solid. So I need another object here at the bottom. So what I want to do is create basically another, I don't know, mesh box or a box, a standard box that I can make this box bigger than the mesh that I am using and reach a height which corresponds to the base of my original mesh. So I'm going to import this boundary representation with this component. I'm going to internalize it, so to get rid of this. And you see that solid point collide asks for a solid, and it says brep or mesh. I do recommend that you always convert these things into mesh objects before sending it to the solid point collide. Okay. So we only miss the points here. The original mesh is this one. I'm going to use a mesh. So we have all the vertices from our mesh, and I will send the vertices to the point collide. Now, a collision object is a strong boundary, a strong condition. So I always recommend that you use a high strength for this collision. Not necessarily thousands, but at least hundreds. Okay. Can also be like this. And this is an invisible goal, so it also goes together with the pressure and anchor points. So what happens when I run the simulation? It happens that when I inflate this, the object cannot expand downward. Oh, let me turn on, well, is it expanding actually? Let me go into the front viewport. I did something wrong. I did something wrong. Toggling false. Toggling false. Sorry, paused. Yeah, rookie mistake. Whoa, okay, no. Yeah, let's start with a low value from the pressure. Let's go here, 3D view. But you see that now this expands, but it can only expand vertically. Okay, well, upward, let's say so. Okay, so you see that we got this this particular behavior here, and these are the rigid lines. I can also tell this to be more stiff, but you see that the actual bending occurring because of the elastic part is actually producing the enough deformation to maintain the rigid springs with their original length, even if the object is deforming like this. Okay, so if you want, in this case, if you want to recreate some kind of, let's say, valleys along these two lines, you could eventually take the actual length of your list A lines. So you must calculate this length multiply it by a multiplication factor. In this case, it's going to be like between 0 and 1. If we want to decrease the actual rest length of our springs. So if I do this, if I decrease this multiplication factor, I'm telling the rigid springs to become shorter. Okay. Now this is something that it makes sense somehow. You can see that the central springs are becoming shorter. There is this kind of very narrow stripe here that has become like thinner, like in this direction and also in this direction. This is not, but this is not a good option, because if you apply a tape, for example, with the initial width, you cannot program this kind of shrinking for your central spring lines. Okay, this is something that is not correct in terms of geometrical consideration for your system. So this should always be 1. The problem in this case is that if you use one single stripe of tape in the central part, this is not enough to avoid this kind of extreme deformation. Okay, so if we apply more tape with more width, then in that case we might have, so it means basically having, let me take a line container so we have an idea of where we are applying our taping. So if I increase this, and remember to do this with the simulation stopped, okay? Because this is a geometric change in your Kangaroo system. So if I do this, let's include also the sides here. I am increasing the taping thickness, basically, or width. And I run the simulation again. And now the rigidity is a little more important than the elastic part, okay? So this structure here is going to inflate, but it's going to maintain some separated behavior between the elastic part and the rigid part. Now, also one consideration, sooner or later, the deformation that is occurring in the elastic way here is going to pull the rigid part upward. So if we go into the front viewport, you see that this is still saying running, running, running. And if we go here in the center part and we take a closer look at this area, you see that this thing is still inflating. And this is because the elastic part is producing well, let's say a pull that is strong enough to move the rigid part of this mesh. Okay, this part of the mesh is basically not changing the length. So imagine that if you applied a taping in this area, which is what we did, okay, the tape is something that is elastic itself, so it can deform. So this width here is basically being redistributed in a shorter area, but with some curvature. Okay, so this is the original width of the tape, but if you shrink this length, then the tape is capable of doing this. This is what's happening. Okay, so these edges here are not stretching; they have the same length, but as there is an elastic action which is pulling, and there is a pressure which is expanding this part here, you see that these lines here are not vertical anymore. They tend to do something like this. Okay, and if they do this, these vertices basically get closer, and so your tape can bend. And if it bends, it also means that it can raise up in the center part. Okay. Now this is true because we are working with scalar values for our forces. Okay. But if you consider, for example, I don't know, some real life material, and I invite you to go to and visit my website. There is a post on working with real strengths in Kangaroo. If you work with real strengths, it means that this value here, the strength for pressure, the strength for elastic properties here, start to be huge. Well, not exactly the pressure value, but the elastic values, yes. So when you work with real strength values, especially for the elastic forces, you will see that these values start to be tens of thousands, okay? Not, well, 11, for example, is totally unreal. Okay, 11, not even rubber has this low value for elastic strength. Okay, so all your values tend to be high. So when you work with the very high values, the deformation that occurs are basically not like this. And also when you work with high values for elastic forces, which are real life value, the strength of pressure must be real. So for example, if you want to inflate this object, you must introduce, well, not 0.1, you start working with Pascal. And in that case, you might want to increase these to very high values, okay? But I'm not going to do this because I'm just interested in the general aspect of deformation produced by pressure. But if you go to my webpage and look for the working with real life forces in Kangaroo, you will see how to set these values properly, okay? I don't want to do this now because if I do this, the simulation becomes extremely slow. Okay, so just so that you see this, if I take, for example, a real life value for the rigid part of my mesh, this means that this can easily go up to, I don't know, something like 50,000, okay, or 100,000, right? Sorry, 100,000. So if I do this and I send this to these high values and reset the simulation and make it run, the elastic part works just fine because you see we have this kind of very small value, which is unreal, by the way. But if I go into the front viewport, this deformation here that is still occurring, you see this edge is still moving up, but it becomes extremely slow. So the result will be an inflatable structure, but you see that apparently you have this different equilibrium, but this is not an equilibrium. In order to see the final configuration, you have to wait for this to say converge. And this is happening in, well, half an hour, being optimistic, okay? So that's why I'm not using real life values for my strengths here, elastic strengths. So, well, actually it was 10,000 and I was working with more or less 1,000. Okay, so in this case, the simulation happens quicker because this deformation happens more fast. There was an observation. Oh, okay, no problem. Yeah. Okay, so having said this, let's create some kind of additional feature for this object. For example, how can I create some kind of inflatable dome behavior, which is something that it's very interesting, okay? So what if I program this inflatable to have a controlled thickness? Because this is the other feature that you might want to consider when you create some kind of inflatable structure. So it's not only create some taping along the surface, but if I create a taping, for example, like this area is going to inflate, this area is going to inflate, okay? I can also take and place a plane or a collision box, as we saw here, in order to make this object inflate only upward, okay? But one thing that you might want to do is also controlling that this object along the taping doesn't change its thickness, okay? So if we create some kind of a boundary condition here that doesn't allow the thickness of this object to change along the taping, then we can program more interesting behaviors, okay? So let's create this, boundary condition here. And how can we do this? Well, of course, we already separated the elastic part from the rigid part. This is the rigid part. Okay, so I want the rigid part not only to be rigid and stiff, okay, but I also want this to be connected vertically, right? So what I'm going to do, I'm going to avoid reaching the edges because I want this phenomenon to happen only in the inner part because this is going to be more interesting from an aesthetic point of view. Of course, you can also reach the edges, but it's going to be a little longer to create these vertical connections. Okay, so I'm just going to simplify this thing by taking the original curves and making this curve like only reach the inner part of my mesh. Okay, so I am reducing the amount of edges, and I'm going to take the rigid part and concentrate it only in the inner part of our mesh. Okay, so this is what I'm doing. So my rigid or stiff edges, stiff springs are only present inside the mesh. So this is going to be elastic as well. Okay. So if I do this, it's easier for me now to create vertical connections. Okay. Why? Because, oh, remember, by the way, that, for example, I now have two sets of lines, right? So let me separate them from the definition. So rigid, elastic. Okay, so I don't care about the elastic. I'm going to hide them for now. If I take a point on curve like this, you see I'm getting this center midpoint for my edges, right? And of course I can take these points here and connect them vertically, but this will be useless because this point do not belong to Kangaroo simulation. Kangaroo simulation is based on actually on these lines because they will be converted into springs, and in the end point of the lines because they are the so-called particles. Okay, so if you go into Kangaroo output, you have the vertices. These vertices are exactly the end point of the edges. Okay, so if I create a connection between the midpoint, this connection point cannot be taken into account by Kangaroo. Okay, so I must use the endpoints. Okay, so if I create vertical connection between these endpoints here, Kangaroo can take into account the elastic force that I bring to these new springs. How can I do this? Because now we have all these edges are grouped together into one single list. So there is no basically separation between the lower and upper edges. So what I need to do right now is basically subdivide this set of, well, actually of points directly between points that lie here at the bottom and points that lie here at the top. How can we do this? Well, either we do it before considering the endpoints or we work with the endpoints. I prefer to do it before because in this case, I do it once and then it will be valid forever. Okay, so I prefer to take a point on curve. Now, yes, I'm going to take a point on curve just to have access, just to access the height of all these lines. Okay, and I will have construct these points, and I will have only two values for the z. Okay, so z is either 4.89 or 3.47. Okay, so bottom of the box, top of the box. Okay, this is always the same values. So I can take, for example, a min max value. Oh, this is a, I'm going to point out that this is an Heteroptera plugin. Okay, so this thing here comes from Heteroptera plugin. I'm going to take the Z component here, and this is basically giving me the two values, the minimum and maximum. Okay, and then I can say, okay, so if this point has minimum Z, then it lies on the bottom of the box. If it has maximum Z, then it lies on top. So what I'm going to do, I'm going to see if similarity. Yeah, okay. So if this Z value is more or less equal to minimum, then it means that that our point and therefore our line lies on the bottom of the box. So I can call pattern the set of lines using this pattern here. And so you see we only get the lines, the edges lying at the bottom of the box. See that the upper edges disappear. And at the same way, if I use if I duplicate all of this thing here and use the maximum as a second number, now I get the upper lines. Okay, So once I have split the edges from top edges, I have top edges and bottom edges. Okay, what I can do, I can calculate the endpoints per each set. And so we have these two separated sets for the upper endpoints and lower endpoints. Now, of course, we have duplicated points because, for example, this point is starting point for this line, but it's end point for this line. So we have duplicated points, okay? So what I would do right now is take a point container and merge these values. Pay attention to this because this is going to be valid also for the bottom part. So if I use start and then end for the first container here, I must use start and then end for the second one. Because if I don't do this, I will have different sorting of the endpoints in this container from this one. And I don't want this to happen. Once I have done this, I go into Kangaroo to utility and take remove duplicate points. Like this and like this. So we have 520 points coming in and 152 coming out. And here the same, 520, 152. Okay, so these are the points that I can connect together. If everything went just fine, I take a line component and connect this with this. If I see vertical lines, it means that I did things properly. If I don't see vertical lines, it means I did something bad in this connection phase here. So what I want to happen during the simulation is that these lines here remain basically the same length. So I want these lines here to be as rigid as the taping I applied to my object. So I will plug them together with the other lines here in the rigid set of lines. So take these lines and plug them together with the other line here. And so we set. And now we have just the mesh, the visible mesh, but if I expand this, now I have the elastic lines, okay? If I expand this, now I have the rigid line that also include the vertical lines, okay? And so if I run the simulation again, let's see it, run. Now we have a strong connection between the lower part and the upper part in this central area. So the pressure can expand these four corners here. And if this four corners starts to pull the inner part upward, everything will move up. Not only the upper surface of the mesh, also the lower surface. You see that now this is increasing in height. And then we have this kind of dome-ish behavior. Of course, if I start to increase pressure, but this is going to push the mesh upward because it's going to push onto the collision object that lies here at the bottom, you see? And this is going to pull the mesh up, especially the sides here. You see that this side is already being pulled up, but this is going to happen also here, here, and on the other hand. Okay, and as there is a rigid connection between the upper mesh, the upper surface and the lower surface, then everything here will simply rise up slowly because of the high values that we are using for the rigidity, the stiffness of these springs. But sooner or later, we will have this kind of dome-ish behavior for our mesh. You see that everything is moving up slowly. If I go into the right viewport, you see that also this part here, see that this vertex is moving up. If we wait enough, you will see that this height is going to be reached also on the other side of our mesh, okay? And also in this from this orientation. So this is a nice way of programming the inflatable structure to behave exactly like we want. Okay. In this case, for example, if we do things properly, there should be no need for the sphere collider. Okay, because if you do things properly, it's very difficult that your mesh would tend to self-intersect. But in case you notice something weird happening, you might want to introduce the spherical light. Now, in case you want to introduce the spherical light, you must work with the spherical light with very low values for the radius, because what you want to avoid is simply that your mesh might eventually self-intersect in these areas where you have more curvature. But you see that this means that we should work with a radius of more or less 1, right? But if we work with the original mesh that we have, there are the sides are actually being represented with more edges, because our initial quad divide was also dividing the polygon representing the height of the box, which was just 1, into 5 polygons. So we have very small edges along the height of the original box. So if you don't want this, you cannot work with this quad divide, because it is also dividing the height of your mesh. You see that, by the way, this is slowly increasing the height. Okay, you cannot do this, but you can work with another approach. I'm going to show you this in a while. In the meanwhile, I also wanted to point out that if you introduce this kind of vertical connection, let me stop the simulation because I want to make some geometric change in my system. If you work with this, let's say, vertical or cross connection, you can also decrease the width or the distance for your attractor, and also work for one single tape, because, or with a thinner tape stripe, because the vertical or the interconnection between the lower and upper part of your mesh is going to introduce another layer of rigidity, you know. So in this case, for example, you might want to double check that you have, let's take a line container. This is the advantage of working with, yeah, okay. So you see that here we are missing something. And I think that this is because our lines lie on the center of our box. So this might produce this kind of thing. Let me see if we can recover. Oh yeah, I think that eventually there is something wrong happening here. So we have all these connections here, and if I double check these lines, oh, the lines are all present. So I don't understand why this is actually producing this kind of thing. Let's reset. Oh yeah, it was just resetting the simulation. Yeah, okay. So yeah, so basically, well, let me do something like this, because eventually we might want to turn off and on the different results. So I just want to see the mesh right now. And also working with a more thin taping will produce a relevant result, because we have the vertical interconnection for our mesh, you see. So yeah, this is something that you can use to program this deformation. For example, let's change things totally, okay? So I don't want to work with a parametric workflow right now. I want to work with some kind of custom behavior, okay? Of course, you can always do this like parametrically, but I'm going to paint, or I'm going to define a differentiated behavior for my inflatable object by hand. So what I want to do basically is create a different splitting for our edges, not based onto these lines here. So I'm going to maintain this construction here, like take it aside, and eventually substitute these curves with other curves. And what I'm going to use, I'm going into Rhino, and I'm going to use this line here and this line here. Little imprecise, but it will work. So I'm going to take curve, set multiple curves, 1 and 2. I have 2 lines here, and I'm going to use them grafted, of course, like here. In this case, there is an empty set of lines. Let's see why it is giving us this. I think the distance was too small. If I increase this, a set of lines appear. Oh, yeah, of course, because now my lines lie at this height. Okay, so this is an error. I must take them and move them at the center of the height of the box, because else I would not intercept the points of the edges of my mesh. Okay, so now you will see that even if I decrease this, I will have no empty set even with the previous values. Okay, and so if I take a look at this, now I have these edges here, and also on the other hand these edges here, and I should also be able to create vertical connection. But for this thing, I must double check that here we have vertical lines. But you see that now we have a problem. Okay, you see that now our connections are being created but totally in a random flavor, because this drawing here is not precise. Okay, so you have different sets of points on top at the bottom. You can also see it by visualizing these edges. You see that these edges have a different amount of edges here. You see that this line is not running along the diagonal. So these edges are considered to be next to the original diagonal line, but these no. And if you have these, you also will have this kind of weird distribution. So this is a problem that can occur. But remember that we want to concentrate this at the center of our body. So I'm going to scale this down and eventually double check that the edges are now symmetrical. Let me see. Here we miss some edge at the bottom. All the rest looks just fine. So what I'm going to do, I'm going to take this point here and move it a little more precisely to here, the diagonal. So you see that if you work by hand, you must take into account that there can be some asymmetry occurring, and you must always double check that things are working properly. Now, in this case, eventually, if we go here, you will have vertical lines, you see? So just double check that this is one problem that might occur in your simulation. So if we work with this, and now run the simulation, reset and run the simulation, you will have these diagonal things keeping your mesh in position. Okay. What happens if I start increasing pressure? Pressure tends to push the object from, let's say, on the base actually. So this object will tend to move up. And as we have rigid or stiff diagonal stripes along the surface of this object, these will tend to form some kind of arch. You eventually would anchor more points on the corner, because one single vertex, you see, it's not enough to keep this mesh under control, especially in this area. You see, this is producing some kind of asymmetric tension inside the object, which is something you don't want to experiment because of the symmetry of the original system. So in this case, you might want to simulate a more efficient anchor situation, which is not just these 4 points here. You might want to take, for example, let's see. Oh, this is something that starts to become more like a topological optimization definition, but it doesn't matter. What I'm going to do, I'm going to take some boxes. Okay, so I'm not going to use the spherical light right now. So I'm going to take just some boxes. We already have well, let's keep it like here. We already have the vertices for our mesh. So I'm going to take a few boxes, set multiple boxes. I'm going to go into the top viewport, like here. And I'm going to draw a box like from here to here and this height. And I'm going to draw another box like here, this height. They don't necessarily must have to be the same height. The important thing is that they pass across the original mesh. Okay, so we have these 4 boxes here. Let's go back to the perspective viewport. And what I want to do is I want to understand if these points, the vertices, lie inside a solid. What was the common in this case? point. Oh, this is, I think it's a nice thing. Point in B reps. Okay. So I want to evaluate if these vertices here, oh, sorry, these vertices here are inside or outside these B reps. Okay. And then I get the inside true, 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 or false, false, false. Let me call pattern like this. And so we have these points here. And I want all these points to become anchor points. So I'm getting rid of this container here and passing all these points to the anchor point function. And so we should have a more controlled behavior on the corners of our mesh. Let's see what happens. Yeah, they are all stuck. They cannot move. This is already keeping things more under control. We still have some, well, a lot of freedom for our mesh here. Actually, it depends also on the fact that I maintain my diagonals very close to the center point. So if we reach with these diagonals almost the corners, then we will have a more efficient behavior for our mesh. But anyway, you see that we already have this kind of arch-ish shape. Also, my diagonals are asymmetrical. Like you see that this is reaching this is closer to the vertex, this is a little farther from the vertex, and also this is closer, this is farther. So you might want to work in a more precise way. You can also create these diagonals here in Grasshopper and be more precise, as we did the internal cross here that we see. But anyway, it's just a matter of precision. So you can eventually, in this case, I would eventually start from here and then start a line with the planner and the project. But before, I want to take the intersection and then activate the project. And then with shift or orthogonal, I go as close to the corresponding vertex as I want, like this. And then I can get rid of the original lines because I can polar array this from this endpoint 4 times in 360. So I have these 4 lines here. And I can also join them together if you want to consider just 2 curves instead of 4, but it's totally irrelevant. And then pass these 2 lines to our curve container. Now this is way more precise than before. It lies always on the at mid height. So let me internalize this data here so I can get rid of these lines, which by the way are still there. And now everything should be more controlled. You see that now we get a more symmetrical behavior. Okay, and so this thing is going to increase its height, and also the symmetrical behavior also depends on the mesh topology. You see that in this case, for example, there is some shifting to the left. Okay, now the problem with this, it also depends on the elastic property. Remember that, oh, well, this is something that we didn't observe. Eventually, I'm going to take a look at it right now. But keep in mind that this object was shifting to the left without reason, because the mesh is symmetrical, the boundary conditions are symmetrical, stresses and forces are evenly distributed, and they are symmetrical. Okay, so why this object is shifting to the left? There is a particular reason that affects all inflatable structures in Kangaroo, which is this one. What I'm going to do, I'm going to take a simple mesh sphere, but not the mesh sphere, but the mesh sphere X, because its topology, it's a little more regular than the normal mesh sphere that I'm going to show you. The mesh sphere is based on the UV division, so it has poles, okay, while the mesh sphere X is basically an inflated cube. So as you can see, that's the cube topology, but it is inflated, okay? So I'm going to take this and I'm going to convert it into a balloon, for example. So let me grab just the solver with its toggle and reset. And what I want to do, I want to give quickly elastic properties to this object. I don't want to differentiate anything right now. So I'm going to give elastic properties to these and also give pressure. And oops, yeah. and this is enough. I'm just taking a higher value for the strength in order for this balloon to don't explode immediately. So I'm going to use elastic and pressure, just these two things here. Okay, we have this thing. Now, the object is perfectly symmetrical, right? And I am using let's say uniform elastic properties and a uniform pressure as well. Okay, so if I fire this simulation, you see that this thing inflates and then starts to rotate and move away constantly in the same direction with the same rotation. This object is basically receiving a momentum from the original expansion, the initial expansion. Because remember that even if pressure says here, you see that this mesh has 150 polygons, right? These are quads. But you see that it says, okay, I'm generating 155 actions. But the pressure always acts on the triangles, okay? So when these polygons start to expand, they expand with some, let's say, direction, okay? They don't expand symmetrically. And there is also an elastic force that tries to keep them compact, right? So when you first release the simulation, Kangaroo simulation, there is a momentum that cannot be avoided. Okay? Especially when you have this kind of irregular shape for the polygons, okay? So even in this case, when this thing starts to inflate, it starts to inflate with some directionality. Even if your mesh is symmetrical and you have a symmetrical distribution for your boundary conditions and so on. Okay, so this is what happens inside our definition. So that's why you see that this mesh expands, and suddenly, if you see this from the front, okay, let's see this from the front. I'm going to draw some vertical lines approximately which corresponds to the boundary of my object. So if I release the simulation and I analyze, for example, this, like this line here, it's evidently longer than what's happening here. Okay, so this is due to the particular momentum that we get from the initial expansion. And this is something that cannot be recovered from the simulation by itself. Now, this is something that occurs especially because we are working with non-realistic forces or strength. Okay, so that's why you get this initial push for this element. Okay, but this is something that eventually you can avoid when you work with real life values. Also, you can also introduce some rigidity along the diagonals of this mesh. Remember that we are working with a UV topology, okay? So UV topology means horizontal vertical, basically. But you can always diagonalize your mesh. Let me turn off the simulation, turn off the final preview. So you can diagonalize your mesh. If we do this, let me do something like Control-Shift this and mesh this. Let's wait for it to calculate. Okay, so we have this situation. We must double check that everything works fine as regards the connection. You see that it's not working properly. This is eventually because of the orientation of the faces inside the sorting of the faces inside our mesh. So let's double check here. We have we have these points with an irregular distribution already. Yeah, because we have naked edges. So remember that the diagonal mesh has this problem for separating the naked naked points, closed points. So remember, we cannot use the naked vertices because even if this is a closed box, right? So we shouldn't have any naked points, but we have, and they are randomly distributed along the mesh. So you see that this is the problem. And this also affects the naked and interior edges. Okay. So in this case, for example, we have the same problem, but in terms of curves or lines. So where there should be no naked edges, we have naked edges. So the interior edges taken into account are only this one, and they also include these edges here. So we have some huge problem happening here. So in case of diagonal automatic diagonalization of this mesh, we cannot do this. So how can we solve this problem? If we want to create some diagonal connections inside this mesh, and we can also, well, we can experiment and triangulate this, but the diagonal connection or diagonal edge come up like in this irregular let's say irregular orientation of the diagonal, so it's not uniform. For example, if I duplicate this and do this, and I take a line, so if I take interior edges, you see that our diagonals happen like bottom right, left to right, well, bottom up, left, right, or top, bottom, left, right. It's totally random, this behavior. Okay, so we cannot rely on this. And if we do rely on this, if we do take these edges here, we will have an asymmetrical behavior for our mesh. So we don't want to do this. So the ideal thing for us would be to have, for example, let's take this thing, right? So the ideal thing would be to have like this diagonal orientation in this area of the mesh, this diagonal orientation in this area of the mesh, and this, for example. Or eventually, we could also create some uniform diagonal behavior like this. For each polygon, consider the two diagonals at the same time. So this will create some uniform and symmetrical behavior all over the mesh. Okay, but this is something that we cannot do automatically. Okay, so if you want to do this, which is something that would be recommendable in order to contain the initial momentum that this mesh is receiving, we could, for example, deconstruct the mesh and also deconstruct. There is a particular deconstruct phase. Here we have it. Okay, like this, and then list item the vertices. List item the vertices, like with corner A, corner B, corner C. This is something that we already saw at the beginning of this lesson. Oh, let me move all of this away because it needs some space, and also we will see if we still need this mesh or not. But anyway, these are the four corners of our mesh, and then we can connect with a line A to B, or start point to end point. The first corner with the third one, and so we have the first diagonal, and then we can also create the second to fourth corner. So what we are creating here is this diagonal connection inside each face. Okay, and so once we have them, we can use them as additional springs. So basically what we are doing, we initially were using only these four edges like springs. So if you do this, for example, if you give a higher stiffness to all these four edges, this doesn't mean that this object can, for example, if this point is anchored, and this is stiff, and stiff, it's not that this square cannot deform. If this point is free to move, like here, for example, then this edge can rigidly rotate like this and like this. And also, these two edges can do this. So this square can still deform, even if the springs are rigid or stiff. But if I introduce this diagonal, and they are as stiff as the four edges, this square can no longer deform, right? So if I consider also this set of lines here, and give them the same stiffness as the rigid springs that I am considering. So I take also these, plug it here, and this I plug it here. So we have now a more rigid configuration for our mesh. Let's see what happens when we release this simulation. Oh, this is something that is totally unwanted. So I discovered later that the problem with this effect was due to an error in the definition of these connection lines at this level. So it was creating interconnection between the four branches of the cross. So that's why the mesh was stretching like in a weird way. But now everything is corrected. I just had to sort points differently in order to create the proper set of vertical connection between the lower and upper part of this cross. So as you can see now, I also added some visualization editing here, and if you run the simulation, you will see that this thing is going to behave properly. And also in a more, let's say, controlled, symmetrical way, you see that the dome-ish effect is being actually achieved the proper way. Okay, so this is the final result that I wanted to end up with.